It's a real pleasure to be here. Some years ago, I had an informal visit, and I'm very pleased to return for a longer visit here, thanks to Edith Falgaron and Michel Perrault for their great kindness in inviting me, and for the splendid hospitality I have received from this group over the last 2 weeks. It's been really fun to be here, so thank you. I'll talk to you about fast reconnection in space and astrophysical plasmas. And as I was telling Emmanuel, that I do not mean to be presumptuous. I apologize to experts who may know a lot more about plasmas and reconnection than I presume, but I wrote this talk with students in mind who may or may not have heard even what plasmas are, let alone what reconnection is. I would like to begin by thanking my collaborators. I have a very large group of very talented collaborators spread out over various age groups, all significantly younger than me. That is one thing they have in common. But in particular, I'd like to cite these 3 collaborators for the purpose of this talk. My work with them is what this talk is about. Scott Ballrood was a former postdoctoral fellow, now an associate professor in the Department of Physics and Astronomy at the University of Iowa, which, as you know, is the home of space physics for many of us in the US. Professor Van Allen established that department, and it continues to be in full force. Ligia Guo was in Max Planck Institute at Göttingen and has very recently moved to the West Coast to Lockheed, where she is working on the IRIS mission. And Yimin Huang, who is a highly respected scholar in reconnection and turbulence theory, who is my colleague at Princeton University. I begin with a very introductory statement regarding the plasma universe. In every textbook, it's often said that plasmas occupy 99.5% or more of the visible universe, and is the 4th state of matter. But really, as far as the cosmic scales go, in most of the universe, plasma is the 1st state of matter. And by a very large margin, it's only on surface Earth and about 100 kilometers or so or less where we actually have anything like the atmosphere, which is not ionized. As you go up further, don't have to wait for 100 kilometers, you already begin to see the ionosphere and its effects. And as you go further and further out, it will become very clear that the Earth is a fragile exception to the rule, that most of the universe is in fact in a state of plasma. So practically all the visible contents of the cosmos, not just stars, but even regions of interstellar dust containing barely 1 million particles per cubic meter, are in a plasma state. The tools of discovery for such systems vary widely, whereas for distant objects, it's nothing but counting photons, and I always admire the ingenuity of my astrophysics colleagues whose entire view of the universe is really made by counting photons and little more. This, of course, is very ingenious, but also gives the astrophysicists enormous luxury, the theoretical astrophysicists especially, because the amount of data is quite sparse, and one therefore can have a lot of models that make sense of the same data. The restrictions closer home are much stronger. And if you go to the heliosphere, in particular to the Earth's magnetosphere, where you have the privilege of in situ satellite data, probing in fact the plasma sea, models are a lot more constrained. This atmosphere also is very collision-less in many ways. In certain parts of the magnetosphere is no more than 1 particle per centimeter cube, a very tenuous system indeed. And then, of course, you have laboratory plasmas, which I don't talk about here, but which have provided powerful constraints for magnetic reconnection studies. ITER, few hours away by a fast train, is such a laboratory plasma. Much more smaller fusion plasmas and laboratory plasmas have been built all over the world, and they're extremely well diagnosed and provide powerful constraints with the data that they have. I will not talk about any of that today, much as I would like to. Magnetic reconnection occurs universally in all these systems, and the knowledge that I share with you today, even though applied to space and astrophysical plasmas, has also had a heavy dose of laboratory plasma work, some of which I'll allude to but not dwell on in depth. Certainly there will be no fusion plasma physics today, though I'll refer to the results of laboratory plasmas devoted to reconnection studies, which have provided some genuine understanding of various things as they go on. And after all is said and done, theoretical models and simulations are in fact a very important tool in our understanding of things. Certainly I, an analytical theorist, when I was first brought up in the tradition of plasma theory, have learned the great value of plasma simulations or high-performance computing simulations, because as you will see today, a number of critical discoveries could not have happened without it. With that, I want to just tell you just a word or two about the tools of the trade. This is a theory talk, heavily guided, I hope, by experimental observation, so I want to reduce it to the basics, especially for the students. So for Newton's law, we are dealing with non-relativistic dynamics here. The plasma is imagined as a fluid, much like hydrodynamic fluid, where momentum on the left-hand side, force per unit volume, is given by rho, which is the density, times dv dt, which is in fact the rate of change of the single fluid velocity v. On the right-hand side, you have the forces operating on the system, J cross B, which is the Lorentz force, minus the gradient of pressure. Written out more explicitly, that ddt operator is actually a sum of two parts. One, which is simply the time variation of density, looking at a particular point in space, but the fluid also has a strong spatial dependence. So the total Lagrangian derivative, ddt, can be written as a combination of two terms. Del del t, which is simply the velocity change in time at a particular point in space, but also an additional contribution that arises from the advection of the fluid elements, and that is v dot grad v. That term that you see is identical to what appears in Navier-Stokes equation, which is hydrodynamic equations, with which you may or may not have familiarity. But some of the most outstanding problems in classical physics arise from this nonlinearity v dot grad v. In Navier-Stokes equations, J cross B is absent. So that's in a way a simpler system. If you drop J cross B, you recover what we call the Euler equation of hydrodynamics, well known to hydrodynamicists. And with the nonlinearity v dot grad v, you have already a very innocuous looking equation that has stumped solution for over 200 years. This has given rise to, as you know, the famous Clay problem in hydrodynamics, which enunciated in the pages of the Clay Foundation. If you're a student and you're aspiring to get rich very quickly, if you can solve the problem of why it is that hydrodynamic systems quickly produce vortex singularities, vorticity is curl cross V, then you will get $1 million for your rewards in this. Unfortunately, the Clay Foundation knows well how to choose hard problems, and so this problem remains an unsolved problem. Just a jump away from it is really the MHT problem. Their current singularities are very similar to vortex singularities, and you can similarly pose a Clay problem for MHT as well. That would only be harder, not any easier than the hydrodynamic problem, though that by itself has its own peculiarities. But be that as it may, I just want to therefore put this in the context of larger unsolved problems in classical physics. Just as hydrodynamic turbulence is an unsolved problem, so is MHT turbulence. Whereas hydrodynamic turbulence requires the study of vortex singularities, be it finite time or not, MHT problems have to deal with current and vortex singularities. And this whole notion that you can have the tendency to form strong intensification of current densities during the time of evolution of an MHT system is a very important effect in the study of fast reconnection models. something that I'll get to presently. Moving on, there is Ohm's law of the kind that you know from basic electricity and magnetism. And in the moving non-relativistic frame by Galilean invariance, you could write E prime as simply eta j. But in the laboratory frame, with the plasma moving with convection velocity v cross b, you have a slightly more generalized Ohm's law, which is E plus v cross b equals eta j. Finally, these three equations can be closed by using Maxwell's equations that you know about. The curl E equals minus del B del T is well known to you. Curl B equals mu 0 J is omitting a term, and that's the displacement current term. That can be dropped for very low frequency phenomena, such as what we're dealing with in the MHD fluid. So those are the equations. You will say, how do you have an equation for pressure? There are two alternatives. You can either think of an incompressible flow, del dot V equal to 0. That then gives you a defining equation for pressure. Or you can assume an isentropic equation of state and use that as your pressure equation. Either choices allow you to close this system of equations. These are the basic elements, mostly, of today's talk. You have the equations. You have a plasma. What is magnetic reconnection now? On the right-hand side of Ohm's law, E plus V cross B, and you saw equals eta j. Eta j is a particular case of what I call R, which I leave unspecified for the moment. And if B dot curl cross R is not equal to 0, then you actually have certain topological constraints that can be broken. And I'm going to just elaborate on this presently. So hold your breath just a little in case I've thrown something at you that is not totally clear. But the manifestation of magnetic reconnection is that if you have two field lines, say the blue line and the red line, pointing in opposite directions, and if they approach each other, they will realize a regime in between where curl of B will get very large. Those are the places where the current density will become very large, and in that region, field lines break and reconnect and form this configuration. This is one that releases the tension of magnetic field lines and liberates a large amount of energy. Now, when I say that the presence of R allows you to break topological invariance, I have to make precise what I mean by that. If you drop the R term, what would happen? You have a celebrated theorem in plasma physics named after Hannes Alfvén, who, as you know, is the only plasma physicist who ever got the Nobel Prize. There have been a number that have been nominated if fusion plasmas would ever become real and produce energy. But we have not succeeded quite in doing that. So a number of very talented people are waiting still in the wings. Some of them have unfortunately passed away. And so we'll have to start the reward system over again. But be that as it may, Hannes Alfvén certainly got his Nobel Prize, and never believe the insult that he got the Nobel Prize only because he was a Swede. Because he, in fact, did very important things in plasma physics, discovered the whole field of magnetohydrodynamics, on the basis of which we are actually doing our work today. Well, Alfvén proved two powerful theorems, which are both very similar in content, though on the surface, they actually look different. The first part of it was the following. Suppose you have a plasma, fully ionized plasma, and you draw, imagine a ribbon that you draw in it, or a circuit that you draw in it. In general, the magnetic field lines will penetrate it, and so you will have a flux in it. You can measure that by taking B dot dA and integrating it over the area bounded by the circuit. Alfvén proved that if E plus V cross B equals 0, then if plasma motion at t equal to 0, taken to be the C1, would even deform the circuit and make it a C2. And this circuit can become very convoluted indeed because of the seemingly chaotic motion of plasma particles. It did not matter. B dot dA integrated over the circuit will be an invariant for all times. This is a powerful constraint. Another way to state the same frozen influx theorem is, imagine that you have a field line, Michael Faraday's field line. I know that turns off field theorists, but it's a very, very usual, a very, very useful way to think of magnetic fields. And if you do think of Hamiltonian mechanics and magnetic field lines as defining a Hamiltonian flow, it would not appear to be so strange, because in Hamiltonian dynamics, we do have particles following trajectories. Magnetic field lines, too, are a Hamiltonian system. It's not very emphasized in electromagnetic theory books, but it has very beautiful properties, Hamiltonian properties, with the Liouville's theorem is del dot B equal to 0. Del dot B equal to 0 does not only mean that you don't have magnetic monopoles. It also means that magnetic field lines are a Hamiltonian system. And therefore, you can think of field lines as trajectories, if you will, for field line flow. Be that as it may, let me continue. Imagine a field line in a plasma, and on top of which are fluid elements attached to it, like beads on a wire. If you start there at t equal to 0, then this means that as you move and the filament deforms itself, the particles that sat on it will sit on it for all times. You cannot decouple the particles from the field line. So this whole question of frozen field theorem is a very powerful constraint on what plasma elements can do in the presence of E plus V cross B equal to 0. So when I mean topological constraints, I mean just that whatever topology that you create the magnetic field in, if you did not put some dissipation in it, you are stuck with it. Nature may have a whole lot of minimum energy states available that the plasma can relax to, but it will not do so in the presence of ideal behavior. You need that R on the right-hand side to break Alfvén's theorem. Alfvén was not a believer of this picture himself. In fact, he fought it, even though he was such a great physicist. And it took a long time for people to persuade him, and I think in the later stages of his life he was persuaded that this is in fact what really happens in many of these systems. Now, so what I have done for you now, I hope, is to tell you what an ideal plasma is constrained to and how in the presence of an R you can break this. So this sort of a motion is forbidden in ideal MHD. Now, let me get to this whole notion of what actually happens when you allow reconnection to occur. You saw this picture that I said when you are driving the system. And in fact, it goes to Dungy in 1953. And Dungy had a very difficult time with Alfvén. But Dungy in 1953 drew this picture. He said, here is a magnetic field topology, if you will, with magnetic field lines pointing in these directions. And remember, this very nice separation is a separatrix. It separates in 4 quadrangles field lines of rather different topology. And if you actually drove it gently, you would form a configuration such as this, where the flow coming in is going to be pushing flow out this way. And reconnection is going to be occurring over a very, very narrow region stretched out, which we call the region of a thin current sheet, where curl B is very, very large. Now you see why the problem of current singularity arises spontaneously in the case of magnetic reconnection. If you squeeze magnetic field lines together, they'll try to come together, and curl B will in general go up. Okay. The question then is, how rapidly can you push these field lines coming together? Why were people interested in this problem? The reason why they were interested in this problem is because back in the 1950s, there were already observations of solar flares. People watched them from a distance, and they would suddenly flare up very rapidly and die away. The process of flaring up took typically tens of minutes. If you looked at, and they felt, and rightly so, even with the sparse observations that they had then, that magnetic field lines were a very important source of free energy in the system. And that some process should tap into that enormous reservoir of energy and convert it into particle energy of the kind that flares typically have. Well, If you allow magnetic field lines and you just think you have some dissipation in it, then you can allow them to simply diffuse. You can calculate the time scale of diffusion of such magnetic fields. That being one way in which you can have energy in the magnetic field converted to, say, for example, heat. But that diffusion time scale is extremely long in the solar corona, because if you actually took the sun's temperature and the density, about which people had very plausible estimates, and plugged it into a well-known formula derived by Lyman Spitzer, the great astrophysicist, then you will estimate that the diffusion time is of the order of 1,000 to million years, depending on what you take to be your diffusion coefficient. Whereas this time scale for flares was of the order of tens of minutes. No way can you make sense of this based on diffusion timescales. So Sweet thought about the fact that in many configurations of the sun, you have field lines that are pointing in opposite directions. And he was after trying to figure out how rapidly you can make these field lines come together. So he looked at a very simple situation. 2 dimensions, assume steady state, incompressibility, del dot V equal to 0, and classical Spitzer resistivity. If you looked at Ohm's law, E plus V cross B equals eta J, Maxwell gives you curl of minus del B del T. So take the curl of that equation, and you get this equation. And the eta J term, which is curl cross J, can be written as 8 over mu 0 del square B. This is now what is called the induction equation. And this has the remarkable property that the highest derivative of the equation, second order, is multiplied by a very small term, eta. Those of you who do asymptotics know that this is a telltale sign that you need to be very careful. You cannot throw away this term like that. If you do that, you reduce the order of the equation by 1, and you do enormous violence to the equation. Much in the same way you do violence to hydrodynamic equation of Navier-Stokes. If you throw away the nu del square V on the right-hand side of Navier-Stokes equation, nu can be small, but del square V can be a very large number. That arises from vorticity, in fact, as you know. So it is here. Due to the presence of very intense current sheet, this term seemingly multiplied by a small eta can be those situations where J is extremely strong. Sweet proceeded to simply calculate how rapidly field line merging would occur in such a system. He threw away del del T, did scaling. V in VB coming in, that's flux coming in, and balanced by dissipation. And he took the estimate as simply 1 over delta, which is the width of this thin current sheet where the current density is very intense. So that's one conservation equation. The second one is mass conservation. Rho is the same. V in times L equals V out times delta. Simple. And then you have steady state energy balance, flow energy coming in, and kinetic energy being convected out, balance. That gives you this V out as V alphane. In other words, V alphane is given by B over square root 2 over the V out is V square over rho mu 0. So V alphane is B over square root of rho mu 0. That's the alphane wave that alphane is known for. You think of the magnetic field as a string, and you wave it. A wave propagates along the magnetic speed. It's like the speed of light in relativistic systems. Plasma physicists love the alphane speed because it is often, in small pressure system, the largest velocity that you can get. So that's the largest velocity with which fluids can be pushed out. But really what measures how rapidly you can push it in is this V in. This V in, can it be as large as VA? That's what people would love, because then that would mean that they can push the flux in very rapidly. Unfortunately, this is not what happens when you simply look at these simple algebraic equations. And believe me, like Kolmogorov's theory of turbulence, this is all there is to the Sweet-Parker theory. Few lines of algebra, and you have a result that has now stood the test of time. So V in by VA is 1 over square root of S. S is a dimensionless number called the Lundquist number, which is typically a very, very large number. 10 to the power 12, 10 to the power 14, 16 is not uncommon for heliophysical or astrophysical systems. Though therefore, the rate of reconnection goes at the square root of s. But square root of s is eta square root. This is important. This is a lot faster than diffusion, because diffusion goes like eta. You are looking at a process that goes much faster than diffusion. But how fast is it? What time scale does it yield? For solar flares, Sweet-Parker takes a year. Time scale is still 20 minutes. So this is a very successful theory, but it's inapplicable. And it's in fact, for 50 years it was believed to be even a correct theory. In the last 9 years, if you read my abstract, as one of those lunch speakers seemed to have done, he said, so you have a new theory, you say. The classical theory is not quite right. So that's what I'm going to tell you about the new theory. But before I get there, let me comment on something else, which is, remember the assumption of steady state that they had to make to get simple results. But most of the time, reconnection in nature is not steady state. It's impulsive. The system is quiet for a long time and then explodes. Solar flare, a slow growth phase and an impulsive phase. This is what I mean. The dynamics exhibits an impulsiveness that is a sudden change in the time derivative of the reconnection rate. It's not enough to just give one reconnection rate. If that is gamma, even d gamma dt is changing, and the burden is on reconnection theories to explain why something is very quiet and then it explodes. The magnetic configuration, in other words, is evolving slowly for a long period of time, only to undergo a sudden dynamical change over a much shorter period of time. Dynamics is characterized by the formation of near singular current sheets, which need to be resolved in computer simulations. This is a classic multi-scale problem coupling large scales to small. And here are examples: magnetospheric substorms, impulsive solar or stellar flares. To this I could add sawtooth crashes in fusion plasmas, but that's another chapter for another day. ITER will have these. But all of you know this. If you've gone to Alaska or to Finland, you stand out and you see, look at the sky. The sky is often bright, and there are sudden auroral brightenings. I'm talking about the suddenness of that brightening, which is what is called a substorm. So this is by an amateur, and in NASA SpaceWeb, if you go web page, they will tell you what phenomenology they think leads to that. So here is the solar wind and its Earth's magnetic field. Here is the dipole field of the Earth. Oppositely aligned field lines come together, transfer flux to the right-hand side, thin out the magnetotail, which then has reconnection occurring, and this has been seen by satellites. Geotail in particular have documented this. And then you have acceleration of particles impinging on the polar caps, giving you the brightening that is an auroral substorm. This suddenness is extremely important. I want to move out and therefore now talk to you about what came about that led to what I would call a new theory. And this is, in fact, the results of our attempt to simulate. So now what I'm doing for you is to show you a high Lundquist number system where we should presumably get Sweet-Parker. And by the way, the Sweet-Parker model has been tested out by numerous simulations by this point. And so I can say that it has a realm of validity or correctness that is unquestionable. However, look at what happens to these simulations, where you will see that a system which had a diffuse current sheets is being gently pushed from the outside. You will see transiently, in fact, a Sweet-Parker current sheet form, but then it becomes violently unstable. And it starts breaking up into these structures, which I call plasmoids, which are regions. If you look within the plasmoids, all the field lines are closed. If you look outside the plasmoids, all the field lines are open. And then there is a separatrix, which separates the regions of open field lines from closed field lines. And this can be brought about only by reconnection. And what you're really seeing is that the thin current sheet is explosively unstable if we exceed a critical Lundquist number, S, which turns out to be 10 to the power 4, 10,000 in these systems. And we find in the simulations, and these results came out in 2009. My group, and in particular I, led that work, but it was stimulated by actually a graduate student's thesis, Nuno Loureiro, in 2007. And yes, feel free.
There's just something that I don't quite understand. So this all is in 2D, right?
Yes.
But like the sun is 3D.
Oh, you're very right. I'll get to that.
Okay.
Thank you for asking. Proceeding by baby steps, the Sweet-Parker model itself was 2D in the first place. So even with the restricted notion of 2D physics, you want to know whether this theory is right in 2D or not. First examination. So and I'll get to 3D. Hopefully we'll have time. I'm not going at a very fast pace, but let's hope that we will get there. What Loureiro predicted was that that thin current sheet is going to be unstable to what he called what he called this instability. He didn't name it plasmoid instability. You can blame me for having coined that word, which has stuck in the literature. But he showed that this is your reconnection layer, and he's showing the linear regime. It was done by a very nice paper, a simulation paper done by Ravi Samtani following Loureiro's theory. So Loureiro identified a very rapid instability of thin current sheets. And he said that's an explosive instability whose growth rate would go up as S goes up, as S to the quarter. His thesis had only the linear instability, and he didn't make any big deal out of it. When he found it, though, after some disbelief, I realized that this is potentially a very important instability. People simply hadn't studied analytically the stability of Sweet-Parker current sheets in the way it should have been studied. And so when he did that, he found that I simply followed through and did the nonlinear work that led to a new regime of reconnection. And that new regime of reconnection, before I get there, I want to tell you, is that this sort of instability has been known. If you go to the Russian literatures, the Russians always get there before any of us do. As you know, they were very good at analysis. If you look at papers going back to 1979, Bulanov did this. He had the idea, but the growth rate was all wrong. So nobody actually found the Loureiro instability with the growth rate. But if you told them back in the 1980s, is there a thin current sheet that can go unstable? Sure, there was evidence. People just did not pay a whole lot of attention to it. And what will it do to the reconnection rate nonlinearly? Now we say that the instability is ubiquitous. We now know that it occurs in fluid systems, it occurs in kinetic systems, it occurs in Hall MHD systems. Every system that we have looked at, if it is characterized by thin current sheets, they will go unstable to the plasmoid instability. So this is one thing to keep in mind as you move forward. Well, in what respect is the prediction of the theory different from Sweet-Parker? Here, what we are doing is to plot the reconnection time of the flux as a function of S. You can see the S to the half plot going up. Time to reconnect flux takes very, very long as S goes to larger and larger values. That's what hurt the Sweet-Parker theory. But what we are finding in the new theory beyond 10 to the power 4 is that the reconnection rate flattens out, and it becomes independent of resistivity or the Lundquist number. The fact, therefore, that a resistive MHD system can by itself get into a regime without the intervention of turbulence, though we will get to that, it has related to this question of 3Dness, and get to a reconnection rate of about 0.01 VA. At 0.01 VA, we are almost in the ball game, not quite. In the chromosphere of the sun, this is enough. In the solar corona, you need something like 0.1 VA. How to cross that extra factor of 10 is what we will get to a little later in the talk. But we are already in an interesting regime without having a lot of turbulence, simply mediated by thin current sheets, which become explosively unstable with respect to plasmoids. It turns out that Shibata and Tanuma, in a very interesting paper, put out this picture, which I found very appealing because it was done before the work of Loureiro and it was done before our work. They called it fractal reconnection, and the picture is amazingly similar to what I just showed you. And It just is that, again, if you go back and look at the paper and look at the scaling laws, there's no prediction of a regime where reconnection becomes independent of eta. There's no prediction of the Loureiro growth rate. But the picture is qualitatively right. It's what we saw. And they saw this in their simulations but did not understand it very well. Uzdensky gave a theory saying that in 2 dimensions, there'll be a power law distribution of plasmoids. And I want to get to that later on. But what I want to show you is some people who are observers will actually ask me, you're telling me all this story about magnetic islands, and you have shown me not sent me a single piece of observation where you actually see magnetic islands. I showed you the picture of the magnetotail of the Earth. This is from Cluster spacecraft. As you know, it was a very successful mission launched from Europe, and in which the US were participants. And this is my postdoctoral colleague, Li-Jian Chen, who actually prior to our plasmoid theory was already tracking magnetic islands in the Earth's magnetotail. And she did very clever diagnostic work. Suppose you had islands, since you don't have images, you have reconnection region like this, and you actually have a crossing of the island in this manner by cluster 2. This is what you will see to be the polarity of the BZ field. What she did was, doing such detective work and combining with the simulations, she actually gave a picture. And she reported in that Nature Physics paper that she saw 10 islands within 10 minutes. That's a lot of islands of the kinds that we're really talking about. And you have electron bursts coming, very rapid impulsive energizations in the presence of these magnetic islands. She said furthermore, and that was surprising, at all channels, you're looking at all these channels, and you're looking at electron flux as cluster 2 and cluster 4 are going past these islands. And she looked at places where BZ actually went to 0. BZ 0 means you're crossing somewhere near the X points here. And she found, in fact, that as the cluster went through, it crossed, there are numerous BZ crossings of null points. And she could therefore map that island topology to her observations and pointed out that the maximum number of particles that were being accelerated were actually occurring at the center of the island, at the O points of the islands rather than the X points. In other words, then, what you're looking at is the very effective role that the plasmoid can play in accelerating particles to high energies. It can similarly dissipate. People who are interested in heating the interstellar medium are here. They're already doing very extensive observational and simulation studies on the effect of turbulence. Their insights into this, on how you can heat the interstellar medium by turbulence, can be further enhanced by understanding how reconnection can aid that mission of the turbulence too. And I was talking to you about SDO observations. These are, as you know, spectacular observations of flares. And if you look at it, you will see that this is the suddenness that you see and occurs in all of this. This is a typical kind of a flaring situation in Solar Dynamics Observatory. It's a spectacular observatory where the images today give us magnetic field topologies of such clarity that they in fact pose enormous challenges for our simulation capabilities. The effort, therefore, to simulate high Lundquist number system continues in this system. We have looked at in the solar corona for systems such as this. What you're looking at is a heliospheric current sheet which extends from the sun, measured width of thickness such as this, length of 4 Sun-Earth radii, aspect ratio of about 50 to 100. Aspect ratio means the width to the length ratio is 1/40. These are the kind of scenarios where you would expect theories such as that to be applicable. We have looked at, in fact, the distribution of plasmoids by theory, and one of my graduate students actually tried to understand if we could see how plasmoid formation would occur in arching flared configurations in the sun. The picture that we are showing here is, imagine you saw these arches out in SDO. Imagine you start out with a vacuum field and you start moving the foot points on the sun. As time evolves, you will form these thin current sheets, which will then break up into plasmoids. if you actually reconstruct using synthetic diagnostic what it would look like for line integrated density measurements, you would see something like this. That's what observers tend to see. And here is the result of simulation. What Ligier-Go found by observing LASCO events is that these observations are the ones that were reported in the literature. They looked at something of the order of several events, and they counted how many plasmoids they see. And there was this turnover, and people actually said that the statistics of plasmoids is log normal. And they made detailed theories about that too. What Ligier found, in fact, is that, in fact, at lower values of plasmoid scale, the magnetic diagnostics in the code predicted a large plasmoid count, but simply by inspection, you undercounted them. And she did both types of tests. So it is not log normal. In fact, it's an exponential distribution. And if you compare it with the theory plot, she argued that all that we are able to do really is to catch only the exponential tail of the plasmoid distribution at relatively large scales. This is plotted as a function of flux enclosed. And if you go further and further in, this becomes a power law that is beyond the realm of present-day observations. Solar Probe Plus, which is going up relatively soon this summer, might be able to do a lot better. And this is Ligier's observations. She's looking at these sort of blobs and using them as proxies for plasmoid coming in. Now I come to your question. So you start with a 2D plasmoid system, and as he said, all systems in nature are 3 dimensions. So what do you expect? Well, what happens is that the initial systems at this, they have extent in 3D. When they're low amplitude, you have what are called flux ropes, twisted things that grow independently. But as the system grows in size, these flux tubes grow in size, they become overlapping, and they produce this Jackson Pollock-like painting frame, if you will, where you begin to see overlap of these islands extended in 3D coming together, and field lines become stochastic, or they become all messed up. This is typical in a dynamical system, which has lost all its invariance direction. If you have this direction of symmetry, you have this nice, well-structured, sharp plasmoids. As you go into the third direction, you find that those flux surfaces are tending to get destroyed. Nonetheless, you can do a mean field type of theory, where you break up the magnetic field into a main 2-dimensional component plus a 3-dimensional part that is breaking the symmetry. And you can construct the flux surfaces for the 2-dimensional part and even try to figure out what is going on in these systems, analyzing some of the tools of 3D. If you project them on the same old plane, you will see, if it was a little darker, you would see better. You see these blob-like objects with blurred outlines. So surprisingly, in the 3D system, you still see some persistence of the 2-dimensional structures. On the 3-dimension, though, if you look at it, it looks very turbulent. Okay? So this is what is happening. Now, if you look at the outflow, this has a channel still, a broadened channel, which allows you greater reconnection rates, broader than the Sweet-Parker channels. And this is what I come to next. Is if you look at this one, here is what we are plotting between, and this is not quite the plot I wanted you to show. I'll show you later on. Yeah, this is the plot I wanted you to show. In a Sweet-Parker flow, you have flow velocities that are in a very, very narrow channel. Turbulence broadens it. Sweet-Parker looks like this. 2D plasmoids have this sort of a play, and the turbulent has a broadened channel of flow. This leads to an enhancement in the reconnection rate. So you say, great. So turbulence is where I want to go, and what is the reconnection rate that I see? Unfortunately, you find that turbulence is not changing your reconnection rate all that much. In the resistive MHD system, with a broadened channel and everything, you still have about 0.01 VA. The morphology has changed as you were anticipating it would. you still have remnants of the coherent structures that we identify so sharply in the two-dimensional system that persist in 3D. Nonetheless, some turbulence theories done by others, such as Alexander Lazarian and Ethan Vishniak, suggest that in a turbulent MHD system, you can get reconnection rate as high as 0.1 VA. We have not found this to be the case in our simulations. What we find, in fact, is turbulence, but that when this turbulence is spontaneously self-generated by the plasmoid instability, then the maximum reconnection rates that we're able to get is still about 100th of V alphane. That may be quite enough for the interstellar medium. It may be quite enough for the chromosphere, but it is not enough for the corona. And what we need to do there is I will get to a little later. What is interesting is that if you ask yourself very simply, is the effect of turbulence, if you average Ohm's law, is to produce this turbulent dynamo term, would the effect be to actually produce an enhanced resistivity? The answer does not seem to be quite that, because the answer is not that the turbulence translates into resistivity, because if you look at the current sheet that is sitting in the middle, that's still quite narrow. In fact, the width of that current sheet is predicted quite accurately by neglecting the effect of turbulence. What turbulence is doing is not broadening the current sheet, is broadening the flow of the channel flow to give you faster reconnection. So there are subtleties here. You cannot model the whole effect of the plasmoid instability by simply going to eta in Ohm's law and say, let's multiply eta by a number, and that will do the job for you. That would be too simple an answer, and I have some other answers that I won't get into here. What is the nature of the turbulence? We have calculated the energy spectra, and so let me get to some plots here, as well as a whole bunch of phenomenology which has to do with the structure factors and so on and so forth. The thing that I want to get to is that there is a very important set of theories that have come about in astrophysics, which are called the Goldreich-Sridhar. Peter Goldreich, well-known astrophysicist to many of you, similarly made a very important contribution to MHD turbulence theory. And he, in fact, argued that the Kolmogorov power law, well known, k to the minus 5/3, which is known to be valid in hydrodynamics, also carries over to MHD. And he gave, in fact, a good theory for it that seems to have high appeal. I want to make a distinction between the kind of turbulence we are generating here and the predictions of the Goldreich-Sridhar theory. I want to point out that the Goldreich-Sridhar theory actually predicts an important scaling law, that k parallel, the wave number parallel to the mean magnetic field, and perpendicular obey this scaling property. And it turns out that our turbulence does not conform to that. This is very different than the kind of turbulence in the solar wind or the kind of turbulence that he has predicted to occur in various other types of systems. This is largely driven by inhomogeneities in the system, because what you're seeing is filamentary structures which become flux ropes, which are driven by inhomogeneities in the system. I think they are what Edith Falgaron would call a state of intermittency in the system, in a highly inhomogeneous system where you have a lot of spatial gradients. And what I want to suggest is that the nature of that turbulence could be different than the nature of turbulence that could occur in a system where you have a uniform magnetic field and turbulence that is slowly decaying. This type of turbulence, plasmoid turbulence, does not fit in very naturally into the classical Goldreich-Sridhar picture. And we have calculated the highly anisotropic spectra, and we have calculated the scaling laws, and you can see that you get k minus 2.17 or 2.36, which are clearly separable from the minus 5/3 prediction of Goldreich and Sridhar theory, which is minus 5. We have calculated these as functions of time, and it evolves, but it doesn't seem to attain for the entire time scale of our simulation the classic spectral laws. How much time do I have? Okay. I want to just leave you with one thought only, which is that 0.01 VA is where we got to with all this work. What would you need to drive it to the next higher level? I just want to say that what happens in these systems is that you generate very, very thin current sheets. And once these current sheets fall below the iron Larmor radius, it is highly questionable that you can apply MHD theory in the first place. and you need to go to what I would call finite Lamo radius MHD or kinetic MHD. You can do it either by fully kinetic means, or you can go ahead and study using a generalized Ohm's law. This was the term, eta j term, written in dimensionless quantities, 1 over the Lundquist number. But when the thin current sheet falls below the Lamo radius, additional terms become important, the Hall current and the pressure gradient terms that you can no longer ignore. When you do the reconnection theory with those terms included, you generate a new phase diagram in which on the one axis you have L over di. L is the system size, di is the ion skin depth, C over omega pi, S is the Lundquist number. And what you have is, through a combination of the Hall effect and the reconnection effect, you can see reconnection rate rising to much higher values. Here, of course, is 0.04, and we have some cases where it even rises up to the order of 0.1. And under these circumstances, you have a number of configurations possible, where in fact you get X-point type of topologies produced in the system due to the Hall effect, with plasmoids being pushed out. That's one set of possibilities. Another is, and this actually possibility has been checked out by Masaki Yamada, and he got the Maxwell Prize in part for this work, where he actually demonstrated that, as predicted by some of our theories, that if you operate in the system of the collisional regime, where the lambda mean free path is less than the width of the current sheet, this is an important small parameter in the theory, then you get Sweet-Parker type of reconnection. But if you go to lambda mean free path greater than delta I, you get X-point type structures of the kind that you just saw with enhanced reconnection rate. Unfortunately for the ISM, this regime seems to be inaccessible, because for most of the numbers that I have looked at, it seems like you do not quite have this one. And on top of this, you have, in fact, ambipolar diffusion effects and things like that that we are talking about separately now. That's going to be a new ingredient in the theory that we should get to. This is just to show you that here is a resistive Hall simulation done by Emin Wong, and this is a completely particle and cell code simulation, fully kinetic. Extended current sheets breaking up into plasmoids. We have done a completely convincing theory, I think, for the resistive MHD plasma. For the collisionless system, people who are good in mathematics have wide open fields where you want to do analytical models for this. Plenty of room for contributions. Try to figure this out. We have great simulation results, and I'm sorry to tell you that in the collisionless regime, we have very few analytic theories. So that's sort of leaving an open question. This is my summary. My summary is the thin current sheets tend to form spontaneously in such systems, and I hope I have persuaded you of that. It is very counterintuitive to think that you start out with a system which has diffuse currents that will tend to form systems with current singularities in it. But if you calculate the energy, believe it or not, counterintuitive it may be, but it is a lower energy state to have a current filament in a system than to have a diffuse current. What gives you the accessibility to these systems is a small amount of dissipation. And what I've shown is they're spontaneously unstable with respect to the plasmoid instability in large systems, substantially exceeding Sweet-Parker rates within the realm of resistive MHD, without invoking Hall current or 2D, 3D turbulence. You saw that. The peak connection rate is very weakly dependent on the Lundquist number. So already within the realm of two-dimensional MHD, you've gotten to the promised land, which is, can you give me a reconnection rate that doesn't depend too much on the resistivity? How fast can you get it? You get 1 over 0.01 VA. Good enough in some cases, not always good enough. The plasma distribution in 2 dimensions follows a power law. The power law appears under-resolved in post-CME current sheet observations which exhibit an exponential tail. This is the exponential tail that we can see. The power law is still in the solar corona beyond the realm of observations. A new phase diagram for fast reconnection has provided some inspiration for new laboratory experiments. This is now under construction at PPPL. This has already been constructed and has reported its first plasmoid observations already. And in high energy density physics plasmas, laser plasma-induced plasmas, which are really a very, very good platform for studying it, where we are studying it as well, but I don't have time to talk about it. Reconnection rate in 2D and 3D are comparable. This may be a surprise, but it is what it is. The energy fluctuations preferentially align with the mean magnetic field. The spectra of magnetic energy and kinetic energy follow a power law, which is neither Kolmogorov nor Goldreich-Sridhar or any of the ones that traditionally people refer to. Turbulence is highly inhomogeneous due to the presence of spatial inhomogeneities and strong flow shear. Phenomenologies such as Goldreich-Sridhar do not seem to apply, and dissipation appears to be important at all scales. Some open questions, and this is where I come back to. It seems easy, almost too easy, to excite the plasmoid instability. Hence, transition to fast reconnection mediated eventually by collisionless Hall effects is easy. Now I'm asking a different question. If you're going to be so easily unstable, do you have enough time to store energy? As soon as you form a current sheet, if it starts disappearing and if it doesn't hang around enough, how are you going to store energy in it? I'm not so sure that the plasmoid instability doesn't get you into trouble in that phase. So an answer could be, don't presume nature comes prepared with nicely prepared topology. It takes time to get nature prepared to have field lines pointing in opposite directions before it erupts. So maybe topology preparation time is the answer? Good question to ask, but we must study nature more carefully. How is energy apportioned between the ions and electrons? This is a very open question in reconnection theory and ISM theory. Yeah, so in MHD theory, you produce a large amount of dissipation, but how are you going to divide up the energy? How does reconnection compare with shocks in efficiently accelerating particles, both in energy and number distribution? Surely shocks also are discontinuities. They too have discontinuous magnetic fields associated with them. But both of these things are occurring. Shocks, though, don't require necessarily reverse fields. Reconnection does. How are we going to distinguish them? What is the proper paradigm of understanding 3D turbulent reconnection, which is often self-generated but can also be forced? Thank you for your attention.
I mean, this very natural turbulence is something very bad for fusion reactors.
Fusion reactors, yes.
Yes.
So
this is the way you see it. I mean, from hearing what you told us, I mean, this seems to be hopeless. No?
No. Can I just tell you why? Okay, so thank you for asking the question. I would have loved to have talked more about fusion plasmas. Fusion plasmas have, at least the kind that ITER has one very strong property, which is that it has a very powerful magnetic field in it. Now, in the presence of this magnetic field, you still have definite evidence from observations, X-rays and others, that you form these magnetic islands. They tend to form on surfaces that are very far apart. The kind of turbulence you need where the islands will grow and overlap with each other and stochasticize field lines occurs in what are called disrupted plasmas. But thousands of plasmas toroidally in tokamak plasmas operate without running into this disruptive limit. If they do, we will have what you say, we'll lose confinement. But the best energy confinement scaling laws are obtained by profile optimization in these sorts of systems, which are not very prone to these sorts of tearing instabilities. And if they grow on surfaces, then they don't get the time to grow to such large amplitudes, but reach a saturation amplitude which is low compared with the separation between the surfaces. So you will often see plasmas with internal islands still exhibiting good confinement properties. I should also tell you that island formation is sometimes helpful, because if you have a lot of impurity accumulation in the center of the plasma, which is highly radiative, then that would actually lead to heat loss. What these islands do have a way of also pushing impurities out to the edges, because they're expanding and they're field line following, and they can get out. So ITER is predicated on realization of optimized profiles, which have been realized in the large US facilities JET, the European tokamak, D3D, General Atomics, the Princeton tokamak. The problem with fusion is not, I think, whether we can operate stably, but as you point out, disruption is important. We have to be careful about that. And if it is disruptive, we're going to lose confinement. ITER is dealing with these issues. I will not tell you that every problem is solved in that respect, but they're working on it. I would say about maybe 60% of the problem is solved, but not 100. I hope that answers your question.
I have a very naive question. Do your plasmoids explain ball lightning?
You know, a colleague of mine who is an expert on lightning, Donald Gurnett, and actually has done this, actually suggested that I look at it. If I look at the morphology, they are in fact suggestive. What is not known all that well is the magnetic field plots during lightning, but if they show regions of reverse magnetic field, they would be a plausible thing. And Gurnett has made the same speculation as you have. I would love to work on ball lightning someday. It's possible. But depends on topology. If the field lines are all pointing in the same direction, there is no chance of plasmoids forming. But if they do have a region where they are, they don't have to be exactly antiparallel, but there's a component of the magnetic field that's antiparallel, there certainly can be. That's what our work shows.
Towards the end of your talk, you mentioned some new experiments which are being motivated by your theory, and I would like to know more the setup, experimental setup, and what you are going to measure and what you plan to test.
So they actually do experiments in what is called, they create two flux cores, and then they generate a magnetic field of the topology that I'm talking about, and they push the reconnection in that topology. I can show you a picture from Masaki Yamada's experimental site, what is called the magnetic reconnection experiment. How much time do I have? I could pull up Masaki's Maxwell Prize address and show you that picture, or I can show it to you later on, because I think our convener just left.
Yeah, so 2 or 3 minutes, I guess.
Let me see if I can pull up very quickly Masaki's he got the Maxwell Prize, and he was humble enough to put himself next to Maxwell and say that he was small. But I want to quickly show the experimental setup. This is the MRX experiment setup. You see the flux cores that I'm talking about? Set up. These are the two flux cores, and the reconnection occurs in between. And they have quantified, this is your plasma going on in this laboratory experiment. This is the setup. And a lot of the data that I was showing you from the laboratory experiments have been obtained in this sort of a configuration. And the data that I showed you, for example, in the large mean free path or the small free path regime was done in this. They don't do it all in one experiment. The density puffing is the way they control the mean free path. So puffing a lot of particles, they reduce the mean free path because it becomes more collisional. They verified Sweet-Parker theory. Then they run the simulation, their experiments in low density setup, high mean free path. That's when they see this other X-point type of topology and larger reconnection rates. I don't think Masaki showed here, no, I don't think he showed here any of the plasmoid results, which are published in physical review letters in this talk, but I wanted to show you a picture. This is a real experiment, and he is a very skeptical experimentalist. But this prediction that if he goes to the Hall parameters, this was a prediction that we made quite some years ago. He grudgingly admits that we were 20 years ahead of the experiment. One of the few times when plasma theory actually predicted something that experimentalists observed later. And so we actually got that right, I think. And it's a very simple criterion. Unfortunately for the Hall reconnection, it's not obeyed in the ISM. Maybe in some regions, like you were pointing out, that this might be an effect. I don't know. I do not know enough about the ISM to rule it out. But he made a table of where these things are applicable. And let me see if I can find the table. Where, I don't know, maybe not. Sorry, I don't have the table. Where he tabulated a whole bunch of systems where the theory is applicable, and applicable to a large number of astrophysical systems, but not to the ISM. As luck would have it. Yeah.
Thank you very much, Professor Amitava.
Thank you.
Bhattacharjee.